Hi, I'm Zor. Welcome to Unizor Education. Well, we continue talking about laws of Newton as part of the course called Physics Plus for all. Now, it's presented on unizor.com, this lecture and many others, including the prerequisites for this course, which is Physics for Teens, and two math courses, Math for Teens and Math for All. Math Plus for all. Now, I do suggest you to watch this lecture from unizor.com, because on this website you find not only the lecture itself, video, but also the textual part of this, which basically is the same thing. It's written like a textbook, and it's always beneficial to watch the lecture and read the same material in the book. Sometimes I might miss something during the lecture, maybe. Sometimes there is a nice picture which is presented in the textual part, much better than whatever I can draw here. And in some cases there are more details maybe in the textual part, something which I can talk about during the video presentation as, okay, this is very easy to prove. You can read about this in the textual part for this lecture. So all the lectures on the unizor.com are separated into different courses. So this course is Physics Plus, that's for all. And basically each course has its own menu, it's menu driven. So it's divided into chapters, and then chapters are divided into some, I don't know, sub-chapters or sections, whatever, and then sections are divided into lectures. So everything is menu driven, and everything is arranged in a logical order. So everything, whatever you are presented in any lecture, is based on whatever was presented before. So it's like the course wherever, like in school and university. So whenever the course is presented, it's presented in a logical sequence. So that's why if you have found this lecture something on the YouTube or somewhere else, I mean, it's good by itself, but you have to understand this is part of the course. Okay. So today we will, as I was saying, continue talking about Newton's law. Well, there are, I would say, two major components in Newton's law in physics. One is first, second, and third Newton's law, especially the second one, when the force is equal to mass times acceleration. And the second contribution of Newton is the law of universal law of gravitation. Now, there was the guy who actually lived before Newton, Johannes Kepler, who invented so-called Kepler's law of planetary movement, and he came up with idea that the planets are moving on ellipses around the sun, and sun is in the focal point of the ellipse. Well, just maybe if you forgot, ellipse can be defined in very kind of a practical way as you have 2 points, and let's say you have some kind of a rope which is fixed in this point and in this point, and this rope, okay? So if you will take a pencil and make sure that both ends of this rope are tight, and then you will start moving the pencil so that basically the lengths of these two segments of the rope is always constant, because this is the rope, so it has certain length. So the length of the rope is always sum of these two segments. And then your pencil will move on the paper around ellipse. Yes, of course there are some more mathematical definitions of ellipse, but this is, as I was saying, a practical kind of definition. So anyway, so Kepler knew what ellipse is, and he basically discovered this law that planets are moving around the sun on elliptical orbits, with Sun being in one of the focal points. So these 2 points are called focal points. And also there is some other continuation of this particular first Kepler's law about something, segment, the area of segments, etc. Let's not talk about this. Our first item which we would like to address is the ellipsoid, elliptical orbit of the planet. So Kepler came up with this only based on observation. He had this astronomy kind of a urge in his blood, and he was observing the planets. He had telescope, I'm sure, and that's what he came up with. And that took him like 30 years or something like this, because he was scrupulously recorded. He was scrupulously recording all these observations, where the planets are in the sky, where the Sun is. And it's not easy, by the way, so it took him 30 years. And so he came up with this particular so-called first Kepler's law. Well, it took him 30 years for observation. I hope it will take much less for us, knowing a lot about physics and mathematics, to basically end laws of Newton, the first law, the second law, the third law, and the universal law of gravitation. So using these laws, we would like actually to analytically prove this. Now, Newton lived at the end of 17th century, like 1680, 1690, whatever. And Kepler was, I don't know, like 60, 70 years before Newton. So Newton knew basically what are the observations which Kepler did, and I'm sure he was basically trying to come up with this analytically. I do not know exactly what Newton did in analytical proof of this. I just have to research. I'm sure it's somewhere on the internet. You can find something like this. It's interesting what exactly he did. But we will do basically the same thing based on Newton's laws. So most importantly, the second Newton's law. This is F is equal to m times a. Well, these are vectors, obviously, and vectors in three-dimensional space. And the second one is that F of gravitation, basically, it's equal to some kind of a constant, one mass, another mass, and it's inversely proportional to the square of a distance between them. But this is a vector. I would like this to be also a vector. Now, r is a distance, not a vector. So I have to multiply it by something like ER. This is a unit vector from point of gravitation, where the source of gravity is located, to the position of the object which we are basically observing. So if you have, this is the source, and this is fixed source, okay? This is my object. We assume these are point masses, obviously. So this is vector r, and vector r is equal to length of this vector times unit vector. Now this is unit vector, which has unit length, er. So that's basically how it's presented. So these are two Newton's law, which we will base our analytical exercise based on. Now, but let's start with a simpler thing. So today we will not prove anything about elliptical orbits. However, there is one very important, I would say, precursor to this. Now, ellipse is a flat curve. Now, planets, Sun and planets are moving in the space, right? So the first question is, why the trajectory of the planet around the sun, something which Kepler observed as ellipse, is flat. So basically it doesn't really go into third dimension. So if you will have a plane, basically, where the object, the planet, actually circling around the sun, well, the word circling is not good because it's actually not a circle, it's ellipse. So moving trajectory of the planet. Why is it in the same plane? And that's what we will basically devote this particular lecture today. It's a very short kind of a proof, but I wanted to discuss all these details before because it's important. I mean, before you basically prove that this is ellipse, let's just talk about the fact that this is all in one plane. So this is the first quality of the planetary movement which we would like to address. So let's just do that. Now, a couple of lectures ago, there was another lecture which was dedicated to central force field, not necessarily gravitation field, as long as it's central. So, our gravitation field is central, and whatever we are talking about today is basically a general property of all the central fields. And the property is that the movement within the central force field, but there are no other forces but one central force, is always flat. It's always within some kind of a plane. That's what we are going to prove today. Okay? So, okay, let's just think about it. Let's consider you have a point where the mass is fixed, and we will actually take this point as the origin of coordinates, Cartesian coordinates in space. Now, let's assume that at some moment t, our object is, so this is O, and this is at point P. Now, this vector is R, and it's obviously depends on time. So as time goes, our object goes from point P to some other neighboring point. And I would like to prove that all these movements will be within the same plane. That's my purpose. Okay. Now, let me just again recall something which was in one of the previous lectures. It was about angular momentum. Now, what is angular momentum? Angular momentum is vector, which is a vector product of r, vector product, cross product, and velocity. Not velocity, sorry. Linear momentum, and linear momentum is mass times velocity. So this is angular momentum of motion. Now, we have proven that in that lecture which I was just referring to, that this angular momentum in a central field, when there is one point where the force actually is emitted, force which is either attracts or repulses or whatever the body, and obviously gravitation field of sun, let's say, considering sun as a point, is of that character. So whenever we are talking about movement in this central field, when the force is as a vector always parallel to vector of position r. So whenever that's the case, then this thing L is constant. So no matter where position is moving and speed is and velocity vector is changing, and that's why the linear momentum is also changing. Whenever it happens, so this is the function of t, of time, and this is the function of time. Position is changing, velocity is changing, and momentum, linear momentum is changing. No matter what it is, L is constant. And you can use just letter L as a vector. Okay, now, we did address it, but I will really very, very quickly prove it again, just for your information. Now, I hope you remember what is the vector product. If you have two vectors, then the vector product is the vector which is perpendicular to both of them, and its length is the multiplication of lengths of these two r times p times sine of angle alpha between them. So that's the magnitude of this vector L, and the direction, as I said, is the perpendicular to two vectors P and R, or if you wish, perpendicular to the whole plane, which is defined by these two. So that's basically the definition of the vector product, and what I will do to prove that L is constant is the following. If I will take a derivative of this vector, if derivative is equal to 0, it means the vector is 0 vector. Well, when I'm talking about derivative of vector, and obviously in Cartesian coordinates, I mean derivative of each coordinate, x, y, and z. So it's just shorter notation, if you wish. Okay, so let's take a derivative d by dt by time of r, and instead of p I will have mv. And v is a function of t. Mass is constant, obviously. What is it equal to? Well, m is just constant, we can take it away outside of this differentiation. And so what I will have left m. This is L of t equals. Okay, so whenever I have a differentiation of vector product, and that's kind of a mass type of thing, and again, if you don't remember, just go back to one of the lectures on Unizor.com, which is dedicated to calculus. So whenever you have the differentiation of vector product, it's derivative of one times another plus derivative of another times the one. So it would be r, I will use apostrophe as differentiation times v of t plus, so derivative of the first times second plus the first times derivative of second. That's what it is. Okay, great. Now, let's think about it. What is v, the velocity? Can you define it based on the position? Well, yes, it's by definition v of t is equal to the first derivative of the position by time. This is apostrophe means derivative by time. So if you, on a straight line, if you have some kind of a movement, you know that the first derivative of the position, of the distance, if you wish, is the speed, right? In three-dimensional, it's exactly the same. It's just by each coordinate. So r is a vector, three-dimensional vector. So you have a derivative by each coordinate as a function of t, x, y, and z. And v is also a vector, also x, y, and z coordinates. But it means that vx of t is equal to rx of t derivative, vy of t, that's y component of velocity, is equal to y component of position derivative, and z component of velocity equal to z component of position derivative. That's what it means basically whenever I'm talking about vector. That's simple. Instead of three different equations, I have one. So that's the definition. So here, instead of v, I can put r of t vector. So position derivative. Okay, great. Now, this is derivative of velocity. What is derivative of velocity? Again, whenever you have a straight line movement, if you have distance, you have speed along the line as the first derivative, and you have acceleration, which is derivative of the speed, which means it's second derivative of the position. So that's acceleration. Derivative of v is acceleration. Again, a of t is equal to v of t, and these are vectors. So if you have vector of velocity and you have derivative by each coordinate, actually you will have the corresponding each coordinate of the vector of acceleration. So instead of this, I can put this acceleration. Now, here we have a central field, right? Central field is characterized by the fact that the direction of the force is exactly the same as direction of the position vector, right? So, according to the second Newton's law, F is equal to mass times acceleration. And this is the vector equation, which means each coordinate is coordinate of the vector of force and coordinate of the vector of acceleration. Each coordinate are related by this equation. So what does it mean? It means A and F are actually collinear vectors, because m is just a factor, it's just constant, it's a mass. So vector of acceleration and vector of f are collinear, and vector of f is collinear with vector r. So what does it mean? It means that between r and a, in a central field, that's very important, the field is central, and that's why we are talking about vector of force to be collinear with vector of position. So in that particular case, in case of central force, r and a are collinear, which means that the angle between them, collinear vectors, angle between them is equal to 0, or maybe they're oppositely directed, then it's 180 degrees. Now, recall that the magnitude of vector product is equal to magnitude of one component times component another component, magnitude of another component times sine of the angle between them. And angle between them is either 0 or 180 degrees. Sine is equal to 0. Same thing here. It's exactly the same vector. Same vector by itself. So it's two vectors which are, again, one on the top of another. Angle between them is 0. So that's also 0. Which means the whole thing is 0. So our derivative of angular momentum is equal to 0. Great. It means that our angular momentum vector, which is again vector of vector multiplication of position and impulse, momentum of linear momentum of movement, is constant. Okay, that's very, very important. Now this is something which I did prove before. Okay, now let's consider again. Now again, P is momentum, which means mass times velocity vector. Okay, so these are two variables. As the object moving, obviously its position is changing and its velocity is changing because of the influence of the gravitational field or any central field. In this case, I don't really depend on gravitational character. It's just any central field. But their vector product is a constant vector. Okay, great. So now let's go back to our picture. This is our mass, the fixed position in space, and I know that somewhere here I have point P, and this is R of t, V of t. Now what I can do is, now I assume that the speed directed not along the position vector, because in this case the movement would be either towards the mass or outside, away from the mass, along a straight line. It's a trivial case, we are not discussing this basically. So the vector of velocity is at some angle with vector of position. So I can always have a plane which goes which contains these two vectors. I can put this vector again from the central point. That's the same vector, right? So from the origin of coordinate, that's where the mass is. And I can always have a plane which goes through this, these two vectors. And the perpendicular to it, which is constant vector L, angular momentum, is a constant vector. It does not move in space. So no matter where our P is moving to, let's say, R of t plus dt. So R is moving, and the speed is also somehow, but their vector product is always the same thing. Well, what does it mean actually? It means very, very simple thing. Let's think again, what is velocity? Velocity is the first derivative of position vector, right? Which is basically increment of position divided by increment of time, which is r of t plus dt. What is increment of position? That's next position in the time incremented by infinitesimal value minus divided by dt, which basically means it's a limit when this displacement of time is diminishing to zero. That's what it means. But in any case, I can put it this way, assuming this is a limit. If it's not a limit, I would put delta, and the limit is usually defined as dt instead of delta t. Okay, from which follows that r from next moment in time, it's a position in the next infinitesimally close moment of time, is equal to r of t plus d of t times dt. Now here is very, very important consideration. This is a vector, this is a vector, times constant, it doesn't change the direction of this vector. So this vector, it belongs to the plane which was defined by r and v, because that's r. And this vector belongs to the same plane, which means some of these vectors would belong to the same plane. Because if you have one vector and another vector, it belongs to the plane, and this belongs to the plane, which means its z-coordinate is zero, basically. If you will multiply it by dt, it doesn't change anything, and the sum of these bicomponent, z component will still be equal to zero. So if I will define the plane between r and v at some point as my xy plane, and the direction where my angular momentum would be z. So in this x, y, and z coordinate system, within x, y, I will have these two vectors, and will have this vector, I will have this vector, and I will have this vector, which means the next position of my object, which is moving inside the gravitational field or any central field, would be within the same plane which is defined by these two vectors. So the plane which I called xy plane is a fixed plane. So movement, whatever the movement was, whatever the position was at point at time t, the point p belongs to this particular plane. The next position in an infinitesimal increment of time would be the same. And obviously the whole trajectory can be basically the infinite combination of infinitesimally small increments. So every one of them within the same plane, so the whole trajectory is in the same plane. And that was the purpose of all these logical derivations. So first and foremost, Kepler came to a decision by observing that the planets are still moving within the same plane. Then he put it on some kind of a drawing, I don't know, and he just decided that it looks like an ellipse. But let me just do one by one step at a time. Next lecture would be dedicated to the fact that this is really ellipse or some other, maybe it's a hyperbola, maybe it's parabola, but in any case, if it's around the sun, the planet, then it's ellipse. Some kind of a comet can come into our solar system. It will change the direction because of the gravitation of sun, but it might not be orbiting around the sun, because maybe it actually flying very, very fast, and sun will not be able to capture it by its own gravitation force. Then this particular comet will just change its course based on the gravitation force, but it will fly away somewhere. So it might be hyperbola or it might be parabola. These are all second degree curves, because they are described on the plane as polynomials of the second degree of x and y. Like x squared plus y squared is equal to r squared. It's a circle. If you have some other combinations of x and y, as long as it's second degree, no more the second degree, that would be the hyperbola or parabola or ellipse or circle, something. So depending on the degree of this polynomial of x and y, you will have different shapes. So if it's a first degree, only x and y in the first degree, then it's a straight line. If it's a second degree, like x squared or xy or y squared participate in the polynomial equation, that would be a second degree curve. And the second degree curves can be, as I was saying, ellipse, parabola, hyperbola. And then there are third degree, etc. What's important about this movement for today's lecture is that within the central field, whatever the trajectory is, it will be flat. So all the movement of the object in the central field would be within one plane. And then I have introduced basically an xy coordinate as the plane where this movement actually occurs. All right, that's it for today. Again, I suggest you to read the notes for the lecture. That's, you go to Physics Plus for all, and you choose the laws of Newton as the chapter or section, whatever, and then within that you can find the lecture called Planet Orbits. I think I changed the name from flat just to Planet Orbits. So I suggest you to read this lecture, and well, that's it. Thank you very much, and good luck.